Okay, now we will start with the next talk, which is Relax Everybody, HTML5 is Secure Than You Think by Sebastian Leikes. So please.
Thank you. So my name is Sebastian Leikes, and I'm here today to substitute for Martin Jones. He's the initial author of this talk, but unfortunately he's not able to be here. And the talk will be about the state of HTML5 security. And before we start, I would like to say a few words about us. So as I already said, my name is Sebastian Leikes. I'm currently a PhD student at SAP Security Research and the University of Bochum. And at SAP, I'm working in the Web Application Security team, which is headed by Martin. And in our team, we are looking into how we can build up tools and knowledge to securely develop web applications at SAP. And we have some specific topics that we are currently looking into. And this is, for example, DOM-based cross-site scripting. We are looking into clickjacking, into secure cross-domain communication, into things like DNS rebinding. Or more generally speaking, we are looking into HTML5 security. And we do so into European research projects, namely WebSynth and Struce. And when we are working in the HTML5 security field, we notice that there's a strange preconception about HTML5. And a lot of people, and especially a lot of developers, think HTML5 is terribly insecure. And then at every hacker conference or security conference, you can see talks about hacking with HTML5 and HTML5 insecurities and so on. And a lot of people are afraid of using HTML5 technologies because of these talks and these preconceptions. But we think that this is unfortunate because HTML5 APIs are perhaps for the first time new browser features that come with a very well-defined security model in mind. And in this talk, we would like to show this security model by comparing the HTML5 APIs that we see nowadays in the browser with the legacy features. So we see that HTML5 APIs were created because people already tried similar stuff before, but before they used some hacks. And we will do so by keeping some score between HTML5 and the legacy features, and we try to see which of them is more secure. And this is the agenda. So in the beginning, I will give a short technical introduction into web applications and their security features that we need to understand for this talk. Afterwards, we will have a comparison of HTML5 and legacy features. More specifically, we will talk about client-side cross-domain communication, about in-browser communication, and about client-side persistency. And in the second part of the presentation, we will also look into dedicated HTML5 security features. So we'll look into clickjacking protection and cross-site scripting protection that is integrated into HTML5. And in the end, I will draw a conclusion. But let's start at the beginning, at the technical background. So if we talk about HTML5, we first need to define what HTML5 actually is, because in general, HTML5 is a buzzword. And every new technology that comes into the browser is labeled with HTML5. And if we look at what HTML5 really is, we can have a look at this picture. And this picture shows the current state of HTML5 as we have it today. And HTML5 was initially created in 2004 by the Web Application Hypertext Application Technology Working Group. And you can see it in the inner circle of this picture. So the inner circle represents the initial HTML5 specification as we had it. And this HTML5 specification was forked by the W3C, and the W3C added some additional technologies. And this is the blue inner circle that we see here. And in the outer circle, you can see a whole bunch of technologies that are related with HTML5 somehow. But if we strictly speak about HTML5, they do not belong to the HTML5 specification. And however, today, as I already said, all of those technologies are labeled under HTML5. And in this presentation, we will follow this buzzword definition. So we regard HTML5 features to be everything that currently comes into the browser that is currently being under specification or standardization by the W3C or the Web Hypertext Application Technology Working Group. Okay, but before we start to go into detail and dive into different technologies here, I would first like to talk a little bit about the basic security concepts of web applications. And one of the most important concepts in this sense is authentication tracking. So in this picture, we see a very simple web application, and this consists of a client and a server. And the client comes in form of a web browser that speaks HTTP to the server. And in this model, authentication is done fully automatically by the browser. So there is, in the beginning, an initial authentication step, for example, a login at the web application, and then the web application creates an authentication credential, for example, a session ID, and the session ID is then stored in a cookie, or the web application uses HTTP authentication, or there's some other form of authentication, for example, client-side SSL certificates. And what the browser actually does is it attaches these authentication credentials to all of the requests that target the web application. Here, for example, example.org. And this is, on the one thing, this is good because the web application does not need to care at all about authentication. So it only has to care about the login and about some authentication checks, but the browser attaches the credentials to all the requests, and the application does not need to take care of it. The problem here is that all requests are automatically outfitted with authentication. And hence, if an attacker is able to create a request in the browser of a victim, targeting here the example.org application, the browser will attach authentication, and therefore this request will happen in the name of the user. And this is exactly the attacker model we are looking at in this talk. So we are looking at the web attacker, and the web attacker is a very limited attacker. So we assume that a web attacker is able to display web documents in the browser of a victim. So for example, you can send an email with a link on it and somehow lure the user into clicking on this link, or can somehow make the user visiting a web page. And then he can create some requests that cause problems at other web applications. And then besides the web attacker, we will also look a little bit on the network attacker, but not too much. And the network attacker is a person that sits in the network and is able to observe or alter traffic that is going to the web server or going to the client. So this is the basic model. And the problem with this web attacker and this automatic authentication is that we would like to avoid that such a web attacker can create authenticated requests towards another web application. And therefore, the same origin policy exists. And the same origin policy is the most basic security principle that we nowadays have in the browser. And the same origin policy restricts traffic that or access in HTTP to elements that share the same origin. So only documents coming from the same origin are allowed to communicate to each other. And the origin is defined by the protocol, the port, and the domain that was used to fetch the document. So here are some examples. So for example, if we have a document from example.com/a, and this would like to communicate with a document residing on example.com/b, access would be granted because the protocol is the same, the domain is the same, and the port is the same. But if either of these three elements is different, the browser will block the request and do not communicate with this. So for example, if we have an application running at example.com that is trying to communicate with an object coming from www.example.com, the browser will block the request. And the same holds for a different protocol and a different port. And this hinders basically the web attacker from creating requests to another application. And now I would like to show what would happen if we would not have the same origin policy in the browser. And here I prepared a small example. So we have a user sitting in front of his browser, and we have an attacker. The attacker is able to set up some website, for example, kittypics.org, where some nice kitten pictures are waiting for a victim to be displayed. And we have a server, webmail.com. And the user is authenticated to webmail.com because he was just reading his email. And in the email, he found a link to kittypics.org, clicked on it, and then he visited the website and sees a nice little kitten on there and is very happy. But if we do not have the same origin policy, kittypics.org could do the following. So it could load a JavaScript, and the JavaScript could start initiating HTTP requests towards webmail.org. And as the browser automatically attaches all the authentication stuff to the requests towards webmail.com would be authenticated, and hence the JavaScript from kittypics.org could read the email at webmail.com or could trigger state-changing actions. So could send an email in the name of the user. So to summarize this, the attacker could leak sensitive information from webmail.com, and at the same time it could conduct state-changing actions. And if we take these two capabilities together, we basically have session hijacking capabilities. And therefore, it's good that we have the same origin policy and that the same origin policy prevents these requests. So if a JavaScript from kittypix.org wants to create requests towards webmail.org, the same origin policy says no. You are not allowed to do this, and therefore the attacker does not have the session hijacking capabilities. So this is the most principal security policy, and now we need to think about this in terms of HTML5. So this talk is about HTML5 security, and if we look at all of the technologies that we nowadays have in HTML5, we need to say, well, interestingly, most of the APIs allow to soften the same origin policy in some way. So we see that there are the APIs offer ways around the policy to make cross-domain scenarios and to exactly make those requests and to fulfill new use cases that are not possible with the same origin policy in its full detail. And so we need to question ourselves, is HTML actually a bad thing? Because if HTML5 weakens the same origin policy and the same origin policy protects us against session hijacking, it should be a bad thing, isn't it? And the short answer is no, it isn't. And the long answer is no, it isn't, because the old ways were worse. And what we see is that the HTML5 APIs are mainly trying to imitate behavior that we already have in the browser. And that there are a lot of hacks that were used in the earlier years to create certain use cases, and the HTML5 APIs offer exactly that functionality that is obviously needed by web applications, but in a secure fashion. And therefore, we would like to compare HTML5 features with their respective legacy features and check how the security looks like and what kind of feature is better here. And we will start with client-side cross-domain communication. And first, here's the problem description. So a developer says, I would like to offer a cross-domain data providing service. And the important thing is, for example, a webmail provider would like to share the address data of the address book with the user with another application, for example, with Facebook.com. And this should happen in the authentication context of the user. So there should not be a general API that allows Facebook.com to extract all the addresses of the address book, but only of the currently visiting user. And hence, this should happen in the browser of the user, where the authentication context is automatically managed by the browser. And we already see this is happening across domain boundaries, and therefore the same origin policy says, no, this is not possible. This is a security risk, so don't do it. The problem is that developers are intelligent and they find ways to work around the same origin policy. And they did so via two different mechanisms, namely JSONP and Flashbase cross-domain requests. And we will first talk about JSONP and then about Flashbase cross-domain requests. So what is JSONP? An important thing to state about the same origin policy is that it is not valid for HTML tags. So HTML tags are not bound to the same origin policy, and hence someone can create, for example, an image tag and use an image from a cross-domain resource to be displayed. And exactly the same holds for script tags. So scripts can be included across domain boundaries. And JSONP is a mechanism that offers an HTTP endpoint that takes a JavaScript callback function and then creates a script that calls that function. And this is a little bit fuzzy, but I explain it here as an example. So we have here an application at example.org, and what this application does, it creates a function, a JavaScript function in its own JavaScript space. And then it simply includes a script from a site that it would like to get data from. In this case, it's flickr.com. And then it passes this function name that was defined over there to this flickr.com domain, and this flickr.com domain creates a script that calls this function and passes data that would like to be shared in the parameter of this function. And then in this function, example.org can do whatever it likes with this data. And so data was shared between flickr.com and example.org in the context of the currently logged in user at flickr.com. And if you look at the security of JSONP, we have to say JSONP is a valid option if we have public data, but is a very bad option if we would like to share private data between two web applications. And the reason for this is that we cannot impose any access controls on this script. So Flickr.com is setting up this script, and Flickr.com cannot control which site is embedding this script. So it could, for example, be included by example.org, so that example.org can have the data and share the data. But Flickr.com cannot prevent evil.com from including this script also. So if evil.com would be able to lure the user onto the web page, it could also access the data of Flickr, and this is obviously not good. And the second problem with JSONP is that you somehow have to trust the data providing service, because you have to include a script, and you're including a script of a third party, and so executing code of a third party in your own web application, so you should somehow be a trusted website when you do that, and not some foreign website that you don't know, or that could be hacked or change the code at runtime. So this is the first cross-domain communication mechanism, and the second cross-domain communication mechanism was introduced by Flash. And Flash somehow integrated a mechanism to opt out of the same origin policy. So we saw that JavaScript is not allowed to conduct cross-domain requests, but Flash is allowed to do it, but only with a good security model in mind. And the security model looks as follows. So we have here a service, C.net, and C.net would like to share data with, in this case, B.net. So what B.net can do, it can load, or what C.net has to do is, at first it has to define a policy, an access policy, and say, in this policy, I allow B.net to access the data on C.net. And then C.net is able to load a Flash applet, and this Flash applet is able to conduct cross-domain requests. And what happens here is that whenever an applet requests a cross-domain request, the plugin checks the policy, downloads the policy file, checks whether B.net is in the policy, and if so, the plugin allows the applet to conduct the request. And then the request is conducted to the data on C.net, and cookies are automatically attached by the browser. And this is a better model than JSONP, because here we can, for the first time, control who is accessing the data. We can say B.net is allowed to access the data, but evil.com is not, what we cannot do with JSONP. And here we can see such a policy file that is hosted by C.net. And in this case, we see that there are two whitelisting entries in this policy telling us that Google.com and Facebook.com are allowed to conduct this request. And this is a good policy because it only allows two domains to do this. But in this policy, we also have wildcards. And wildcards are really bad because wildcards basically allow all the domains in the web to conduct cross-domain requests. And therefore, wildcards basically opt out of the same origin policy. So if you use a wildcard, you basically deactivate the same origin policy for your site, which is a bad thing because without the same origin policy, we have session hijacking capabilities. And we wondered how common this is, and we conducted a study on those cross-domain policy files. And we conducted a crawl and downloaded the cross-domain XML files for 1 million web pages for the Alexa Top 1 million. And in total, we found about 83,000 of them. So not all the sites have those policies. And we found out that about 31,000 simply contained a general wildcard. So about 37% of those sites simply opt out of the policy of the same origin policy. And what we see here in this graph is that the cross-domain XML feature is mainly used by the big sites. So we see in the Alexa top 10 to 50,000, we have a percentage of 30% using this mechanism. And we also see in the red curve that a lot of those sites are using wildcards. And this is a very bad thing, and developers are mostly not aware of those wildcard problems, and therefore putting wildcards into those applications. And now, so these are the two legacy mechanisms for cross-domain communication, and now we will have a look at the HTML5 way of doing things. And the HTML5 way is coarse, or it's long written, it's cross-origin resource sharing. And cross-origin resource sharing is very similar to the Flash approach. So it's also a whitelisting mechanism. So the receiving server, so the data provider, has to whitelist the sites that request a cross-domain HTTP requests, but CORS has some advantages over Flash. And the first thing is CORS still allows wildcards. But the good thing with CORS is as soon as you put a wildcard into your policy, there will be no authentication credentials that you can send. So as soon as you request authentication credentials to be added to your request, you are not allowed to use a wildcard. And this is a very good thing because you cannot, a developer that is not aware of this fact cannot break security by putting a wildcard into his policy. And another good thing, of course, is that it allows a much finer access control. In Flash, we can only whitelist one domain for accessing all the resources on another domain. And in CORS is HTTP header based, so you have to give an HTTP response header back. You can whitelist on a resource level. So you can say, well, this script is allowed to be accessed by this domain, but this script is not allowed. This is nothing you can do with Flash. And if you look at how far CORS is widespread, we have to say, well, CORS is very widespread in all of the current browsers. We have CORS, and in the future, we will also have CORS in all of the browsers. So if we think about security and think about our score, we have to say it's 1-0 for HTML5. Okay, so let's have a look at the second field. So it's in-browser communication. And in-browser communication is very similar to client-side cross-domain requests, but still a little bit different. And the problem here is that a developer would like to communicate with a cross-domain request. So we have a website, and in this website we have a frame, or we have a pop-up window, and the one window should communicate with the other window. And, well, it's a cross-domain window, so it's coming from another domain. So the same origin policy says, no, you're not allowed to do this. It's a different domain. This is not possible. And developers are intelligent, and they said, well, we'll do it anyways. And they found a few methods to do this, and we will talk about hash identifier parsing and window name in this talk. So let's first speak about the hash identifier thing. So here you can see a URL from example.org, and the thing that is written in bold is the hash identifier. So everything behind the hash sign in the URL. And the hash sign points normally to a local anchor. And the good thing about this hash identifier is that if you reload a URL and only change the hash identifier, there's not actually a reload happening in the browser. But it just changes the hash identifier, and you can extract it via JavaScript. And the communication technique that can be used to make cross-domain communication is that you have a window and a frame in the window, and the window is able to navigate the frame. And on the other side, the frame is able to navigate the window. So what people are doing is that they are navigating the parent window or the frame to the same URL, but with a different hash identifier. This does not cause a reload, but the frame and also the window are able to access the hash identifier via JavaScript. So you can implement a polling and ask whether the hash identifier changed every half a second or so, and then check whether there were some messages exchanged. And this is a way how cross-domain communication can be done, although this bit of the SOP. The second mechanism is the window name property, and the window name property is a DOM property, so it can be accessed via JavaScript. And the strange thing about this window name property is that it can be set and read across domain, so it does not adhere to the same origin policy. So it's one of the only DOM properties that does not adhere to the same origin policy, and people are using it to communicate. So for example, if you open a pop-up, you can give it a name, and the pop-up can access the name. And the opening window of the pop-up can also change the name and read the name. So this is one property where the two windows can exchange data from. And hence, it can be used for in-browser communication. So now let's look at the security of those two mechanisms. And here we have two security problems. The one is authenticity, and the other one is confidentiality. So authenticity, because we do not have any proofs about the sender of a message. So we can change, we see the hash changed, or we see there is some information in window name, but we do not have any proof who wrote the data there. So it could, for example, be another website, evil.com, that changed the hash identifier. And we are not aware if this was the trusted application that we host for ourselves, or if it was an evil application somewhere else. And confidentiality is another problem. So for example, window name is readable across domain boundaries. And it also it maintains its value even if you do a reload. So if, for example, you use window name for data transfer or in-browser communication, and an attacker can navigate away the window to another evil website, for example, evil.com, evil.com is also able to access the data in window name. So that you don't have a guarantee that the data that you are sending across domains is secure. So now let's look at the HTML5 feature. And the HTML5 feature that is able to do this in-browser communication is the post message API. And the post message API is basically a mechanism similar to the two I presented before, where two frames or pop-up windows can communicate with each other. And it's very simple. So the receiving website simply registers a callback method for the message event. So it's a method, and whenever a post message arrives, this message is called, and then it can do stuff with the data in the message. And to send the post message, there is a post message function. You only need to have a window handle, so you can simply read an iframe from the DOM, or you can open the pop-up, you get a window handle, and on this window handle you can call the method post message. And the method gets the message that you'd like to send and the target origin. And if you invoke that method, then the event handler of the window that is pointed to by the window handle will be called, this event handler. And the post message API has very strong security guarantees. So it provides confidentiality. So the browser ensures that only the target origin is allowed to read your message. So when you send a message, you can type in a domain and say, well, I only want, for example, example.com to read this message, but not evil.com. And then only example.com will receive this message. Furthermore, it provides authenticity because the browser adds information about the origin of a message. So when you receive a message, there is a field called origin, and you can read that field and check where the message is coming from. And then you can, this is unspoofable information, and you can check whether the message is really coming from a trusted source or whether it's not coming from a trusted source. And it also provides integrity. So the method cannot be intercepted by any third parties, also not by a network attacker, because it's not leaving your browser. So if you look at this and look again at our score, to say it's the second point for HTML5, it's much more secure. Okay, now let's go away a little bit from communication, client-side communication, and have a look at local persistent state in the browser. And again, the problem is the developer would like to permanently store data in the user's browser for whatever reason. Well, we have the same origin policy and says, no, you're not allowed to do this because all the local state is, you have to put it into files, and files are not, cannot be accessed via the HTTP scheme, so we have different schemes. You're not allowed to do this. Well, and the developer says, well, I do it anyways, and he does so via cookie hacks. And cookies are the only mechanism how a web application can save data in a browser, at least in the HTML4 world. And how this works is, so the cookie is available via a JavaScript API called document.cookie, and so a web application on the client side can simply write data into this cookie value, and the data is stored in the cookie. However, if you think about the purpose of a cookie, then this is to maintain a state of the server on the client side. And so a cookie is sent to the server each time a request is made. So if I write a cookie, my information is transmitted all the time to the server. And if it is a little bit more data, we cannot really save bandwidth with that. And if you look at the security of these cookie hacks, we need to first look at the same origin policy, and cookies do not really adhere to the same origin policy. So they ignore protocols, and they also ignore ports. So they are only looking on the domain or on the subdomains. So if you if you define a cookie on one domain or on one application running on one port, it is also accessible via another application on the same server, either accessible via HTTPS or via a different port. And therefore, if you have a cross-site scripting on a subdomain, an attacker can extract the cookie of another domain through the subdomain. Or if you have a cross-site scripting in another service running on another port, the attacker can also extract the cookie. And then here we have the network attacker also, because the cookie is sent to the server each time you make an HTTP request. The network attacker can simply make your browser to create an HTTP request, wait for the HTTP request, and then extract the cookie values from it. So the network attacker is also able to access this data. So now let's look on the HTML5 way of doing this. And in HTML5, we have a new JavaScript API, and it's called the Web Storage API. And one part of the Web Storage API is the Local Storage API. And this API provides access or a separate data space for each origin in the browser. So we can see an example here. So we have the local storage. We can store items in the local storage. Then we can do something else. For example, close the browser, reopen the browser. Afterwards, we can get items again from the local storage, and we can also remove items. And the local storage adheres strictly to the same origin policy. So each origin gets its own browser storage area assigned to it, and you cannot access the storage of another web page. So an application running on another port is not able at all to access the local storage of another application on a different port. So we again look at our scoring. We have to say it's the third point for HTML5. And now we talked about HTML5 features in a functional view. So from a functional point of view, where HTML5 provides functionality, and this functionality has some security model in mind. Now we would like to look at HTML5 security features. So dedicated features that were introduced into the browsers lately to protect against certain threats and attacks. And the first thing that we will look at are click-checking protections. And click-checking, or also called UI redressing, is an attack when an attacker tries to steal a click from a user. So by circumventing somehow the same origin policy, a site that should be attacked will be framed by the attacker, then the frame will be made invisible, and then there will be some other button behind the frame, and if the user believes to click on a button, he actually clicks on the invisible frame, and clicks a button on the invisible frame, and then a click is stolen. And a lot of web pages protect against click-checking, and the legacy way of doing so are JavaScript frame busters. And here we can see a very naive and broken implementation of a frame buster. So this is a piece of JavaScript that you can embed in your site, and the site simply checks whether the parent frame is something different than the own frame. And if you are in the top level, this equation will fail, and you will not carry out the next step. But if you are being framed, this will return true, and therefore it redirects the parent location to the own location. So the frame is reloading itself in the top browser window. And this is the way of doing it, but there was a paper a few years ago, and they showed that this is completely broken. So there are several ways of preventing this frame buster from working. And basically there are two strategies. So you can either prevent the JavaScript from executing, so for example via HTML5 Sandboxed Iframes, or via misusing cross-site scripting filters, or you can prevent the redirect from happening. And there are techniques. One is called 204 flushing. Then there is a technique called double framing, or by simply asking the user. So if there's this navigation event taking place where the frame reloads itself, you can ask the user and say, well, would you really like to leave that web page? And if the user clicks no, the redirect will be canceled, and the frame buster fails. So it is possible to build secure frame busters, but the knowledge is not very widespread, and it's quite difficult to do it. So now let's look at the new browser feature that does this, and this is the Xframe options header. And the Xframe options header is very similar to the JavaScript frame busters. The idea is the same. So we would like to prevent an untrusted site from framing a site that we control. And we can do that by outfitting this page with an HTTP response header. And this HTTP response header will indicate to the browser that framing is not allowed for this site. And as soon as the browser sees this HTTP response header, he will prevent any other site from framing the site that is outfitted with this header. And currently, there are, I think, not many known vulnerabilities, almost none, that can prevent Iframe options from doing what it is supposed to do. So if we again look at our score, it's 4-0 for HTML5. And now the last round, it's about fighting cross-site scripting. And well, cross-site scripting is known for a very long time. So actually the first advisory that we saw about cross-site scripting was written in the year 2000. And I think the problem is also well understood. So we know what are the consequences of a successful attack and how can we prevent cross-site scripting from happening. But however, we are still not able to really address the problem properly. So for example, there's a yearly report by Whitehead Security, and in this report you can read that 50% of all the vulnerabilities they find in security assessments are cross-site scriptings. And we also conducted a study specifically focusing on DOM-based cross-site scripting. We did this year, and with our tool we were able to cross-site script 10% of the Alexa top 5,000 in a fully automatic fashion. So cross-site scripting seems to be a big problem, and HTML5 tries to address this problem. And there are two dedicated features to do so. There are the Sandboxed Iframes, and there's the content security policy. And let's first talk about Sandboxed Iframes. So Sandboxed Iframe is basically just a normal iframe, and you can put an attribute into the declaration when you write it in HTML, in the sandbox attribute. And with this attribute, you can prevent JavaScript execution from happening inside the frame. And you can use this feature to fight cross-site scripting. So whenever you have user input that you would like to display to a user, you could simply put it into a frame and then add the sandbox attribute to the frame. So even if the user is able to inject some JavaScript into the frame or into the application, it will not be executed. So it's some kind of sandboxing technique where you can sandbox untrusted user input. This is the one strategy. And the second mechanism is the content security policy. And the content security policy is currently a very promising security technology. And basically, it's a whitelisting mechanism. So currently, if an attacker injects scripts, the browser cannot decide whether this script is a legitimate script or whether the script is a malicious script injected by the user. And what a host needs to do if he uses the same origin, the content security policy, is that he provides a whitelist of script hosts. So he says, well, I would like to accept scripts from example.org, from google.com, and from facebook.com, but nothing else. And then this policy is sent to the browser, and the browser enforces that only these scripts are executed, or scripts coming from these hosts. And you're not allowed to do inline scripts anymore, so you have to extract all your scripts into external scripts, and then you can whitelist all the scripts. And now if an attacker has a cross-site scripting injection vulnerability, he can inject the script, but the browser is able to detect that it's not a whitelisted one, and then it will not be executed. And if we look at the score again, so we have two novel security features that were not available before. We give another 2 points for HTML5. So it's 6-0 for HTML5. And with this, I would like to conclude. So what we see is that modern browser APIs realize needed client-side technologies. So technologies that web applications really need and that web developers already used before, but in an insecure fashion. But this time, we see that these APIs are designed with a solid security model in mind. And it is still possible to make things insecure with HTML5, but it's much more difficult. So because most of the HTML5 features are secure by default, while the legacy features are not secure by default. You can also make the legacy features secure, but it's far more difficult than with the novel technologies. And if we look at the functionality, we see that the HTML5 functionality is even superior to the legacy functionalities, and we can do much more and realize new use cases that we were not able to realize before. Okay, so thank you very much for your attention, and if you have any questions, you are free to ask.
So thank you. Are there any questions? Okay.
With all these new features, usually the point is, what's the kind of browser support for all this? Can I afford in a busy website to rely on these features yet, or what's the current state? What's the percentage of users I kick out by relying on this?
The answer, it depends. So it depends on what you'd like to support. So I think a problematic browser is still IE8. So it does not have all the features included. So if you would like to support IE8, it's a little bit problematic, and then you have to switch back to the legacy features. But if you speak about modern browsers, so browsers that we have nowadays, the features are there in all of the browsers. And IE10 and IE9 also have all the features. But I have to say HTML5 is a living standard. So it's still under development. It's already implemented, but there are still slight changes. But I think most of the core functionality, which I showed in the first, we can show it in the first picture, in this one. So this is the current state. So this picture is from January 2013, and it shows the majority of HTML5 technologies. So the greener the color is, the more mature the technology is. So the dark green is already a W3C recommendation, and everything below is shortly before becoming a recommendation, and red is still a working draft. And so you can see that the core functionality is almost green, and you also see that some technologies are also already a W3C recommendation.
So any other questions?
Thank you for your talk, and I would like to add a comment. I'm a little bit concerned about the message you sent, especially in the last topic, that the browser will cover the feature of cross-site scripting. So it seems that we fight always the laziness of the programmers to do correct input validation, output validation, and now you say, okay, don't care about this, just use HTML5 and all will be fine.
Yeah, that's a critical point. That's completely right, and the content security policy should only be seen as a second line of defense. So the setting or the idea behind the content security policy is that you cannot avoid vulnerabilities. So you do the best effort to avoid them, but there will also always be security vulnerabilities, and you're not able to hinder them. And the CSP is a second line of defense that helps you to protect against exploitation of these vulnerabilities. But you should definitely not stop to fix vulnerabilities when you see them. And there are already a lot of bypasses for the content security policy. I'm aware of at least 20 of them. So I think this is just an arms race, like data execution prevention and ASLR was added to operating systems. CSP is the first step of having a mitigation technique in the browser, and I think smart people will find ways around it, and it will hinder some attackers from exploiting vulnerabilities, but it will not totally hinder attackers from exploiting stuff.
Yeah, I also have a question about the last part, the cross-site scripting part, where you say two things. First of all, if it's outside content, place it in a secure iframe. How do you know if content contains user input? You can't know that. If you display database data, which is mostly done in applications, you never know if the database data originates from the user or somewhere else. So you would have to basically protect all content against scripting, which means you cannot use scripting anymore.
That's partly correct. Of course, you're right that you do not know any kind of user input your application processes, but there are certain neuralgic spots where you know it. For example, if you provide a guestbook service or something like a Facebook wall where users can post comments to, you know that the comment is user input. You exactly know it, and you can simply wrap it in such an iframe, sandboxed iframe, and nothing will happen. Or another example for where you can use sandboxed iframe is advertisement. So what we currently see is that advertisement is used via script includes. So you simply include a script include, and then it writes the advertisement into your page. And you have no control what the script is doing. It could do whatever it likes to do. It could steal your cookie. And with Sandboxed Iframe, you're also able to allow, it was a little bit simplified, you're also able to allow JavaScript. But you can say, this is something that is not allowed to access stuff in my domain. So you can use a script from an advertisement provider, put it into a Sandboxed Iframe, and although it is hosted on your page, it's your HTML code, you can say this HTML code is not allowed to access the HTML code outside of this sandboxed iframe. And therefore you can sandbox such components without having the risk of them stealing your private information.
So, any other questions? So, it looks like we're done. So, thank you.